All right, so now we're going to talk about how to develop line search algorithms on manifolds. And line search algorithms are, of course, one of the simplest optimization algorithms one can develop in vector spaces. And we want to see how we can extend this to the setting of Riemannian manifolds. Okay. Okay, so so let's just try to recall it's like what a line search algorithm looks like on our end. Okay, so it's based on the following update that the new candidate point, it's like for your optimization algorithm, is expressed in terms of the old point plus some time step times a search direction. So this eta k is the search, well, which is in Rn is the search direction. Okay, and then in Tk, which is obviously in R, right, is the time step. Well, let me rephrase. Let's call it the step size. Okay, and then of course it's like the goal is to generalize this. It's like to a nonlinear manifold. So you want to and of course one of the problems, if you will, with generalizing this to a nonlinear manifold is that this update algorithm or this update which we have, it's like it involves or requires you to take advantage of the linear space structure of Rn, right? Because you're going to take a vector, you're going to multiply it by something, and then you're going to add it to a position. So the question is, well, what's the right way to generalize this? Okay. So how to generalize this? So one generalization of this, is that, let's consider a nonlinear manifold. Consider manifold M, right? And you want to, so the search direction, so let's maybe draw a picture here, right? So now we have a manifold M, you still have a point xk, right? And you want to do a new step here. And you want to search in a particular direction. So we talked a bit about the idea of tangent spaces. So it's very, very natural to consider a search direction which is an element of the tangent space. Okay, so you consider manifold, and we want to select a search direction eta k, and then this is going to be in the tangent space to this. So this is in T xk to the manifold, right? And then you search along a curve, right? Let's say gamma, okay, in the manifold, right? Whose tangent vector is eta k, right? Whose tangent at t equals to 0, right? Which is of course just gamma dot or gamma prime if you prefer. And 0 is equal to eta k. Okay, so and then the question is, well, how do you construct it's like this this curve, right? So the question is, construct such a curve. Gamma. Okay. And the way we're going to approach this is to introduce a new structure on the manifold, which we'll call a retraction. And then what the retraction does then is a way to relate, it's like this tangent vector with a curve in some appropriate sense. Okay. So the answer, the partial answer to this is that we will use the notion of a retraction to construct such a curve. Okay. Okay, so we'll explain a little bit. It's like what this idea of a retraction is and where it comes from, and examples of that. Okay. So let's talk about retractions. So before we do that, let me perhaps say it's like, how one might choose, for example, search directions in line search algorithms, right? So conceptually, right, the easiest, sort of the simplest way sort of to optimize a differentiable function is to sort of translate the test point x of t, right, in the direction of steepest descent. Right, so this is analogous to trying to go down a hill as fast as possible by, at every point, it's like trying to find, it's like locally, it's like which is the path which makes you descend at the fastest rate, right? And that is, of course, by definition, given by the negative of the gradient of f(x). And you do this on the constraint set. And then until sort of one sort of reaches a point, it's like where the gradient vanishes. Okay, and then the points, it's like where the gradient vanishes, are what are called critical points of the function. Well, either stationary points or critical points. Of f. Okay. And so what's sometimes helpful is to think of the optimization algorithms which we try to implement as being something like a numerical time discretization of a differential equation, right? So that's consistent with this idea of having a test point which sort of moves along the search space sort of continuously in time, right? And you can sort of ask, for example, what kind of differential equation it's like you want the, it's like this test point function to satisfy. And then once you have a differential equation, you could then try to discretize this using a variety of ways of, it's like approximating the solution of, it's like initial value problems, for example, right? So, so if you have continuous gradient descent, right? Right, that's described. By the following equation, right, which is that x dot at t is equal to, so at every point you want x dot to move in the negative gradient direction, right? Maybe let's call it gamma, right? So gamma dot is equal to negative the grad of f, and then it's evaluated at the point gamma of t, right? And you want this to be true for all t, for example, right? So this is an example of the continuous gradient descent equation, and you probably know it's like there are such things as Euler discretizations of a differential equation, where if you have, say, x dot is some f of x, for example, that the forward Euler discretization is xk plus 1 is equal to xk plus some time step h times f at xk. So, of course, this looks very much like the line search algorithm, which I just erased, right? That the new candidate point is equal to the old candidate point plus some multiple of a vector, if you will. Okay, so here the vector or the search direction, as we talked about before, is negative the gradient of f at that point. Okay, and so what sometimes happens is that one thing you could do if you're trying to prove that your numerical algorithm has certain rates of convergence is to maybe first prove that the solution of the continuous differential equation has a certain rate at which f of gamma of t decays, right, as a function of time. And then say that, well, okay, this, say, Euler discretization is accurate to the exact solution of this differential equation. It's like to a certain order of accuracy. It's like in the time step, and the combination of the two then allows you to conclude something about the rate at which this numerical method converges to the minimizer. So that's one possible approach to doing these kind of things. Okay. So again, the problem we have here, which is sort of what the issue of retractions is trying to address, is this whole question of how do you move in a particular direction, okay, along the manifold. And so one possible resolution to this, if you will, is of course if on a manifold you have coordinate charts. So if you choose a coordinate chart on the manifold, then of course that locally endows the manifold with a linear structure, which comes from the linear structure of the Euclidean space you're locally identifying. It's like a neighborhood of the manifold with. And so you can sort of go back and forth, it's like between these two things in order to, it's like do this kind of additive update, if you will. Okay? And so you don't, as it turns out, you don't quite need, it's like there's a, let me rephrase that. It's like, as it turns out, there's sort of a related structure which you can think of as being related in some way, shape, or form. It's like to a coordinate chart. It's which we will call a retraction, which will do something quite similar. Okay, so let me sort of just say what it is. Okay, so a retraction let's call that R, right, at X, right, and you denote that by R sub X, right, so you're going to sort of, well, I guess what's basically happening is that you have a retraction which is maybe defined everywhere in the manifold, but you're interested at how it behaves. It's like at the point X, and you look at the sort of restriction, if you will, to the point X, it's, I guess, and you denote it by R sub X. And at R sub X, it's like this is a mapping Txm to M, right, with a local rigidity condition. Okay, so so in particular, what it does is that that preserves gradients at X. Okay, so so the problem, if you will, is that if you had sort of just used a coordinate chart to endow a neighborhood of the point X with a linear structure, right, you could potentially break this condition that you know, shifting in that direction results in a at least, you know, low order decrease, it's like in the cost function, right? So what do I really mean by that? What I mean by that is the following. Okay, so what's the picture here, right? So the picture here is the following. So say again you have xk, you have a vector, it's like eta k, which is in the tangent space. And what you want to do, in essence, is that you want to look at Txm, and you want to identify it with some neighborhood of points on M. Okay, and so the retraction Rx will take the vector eta k and essentially give me a new point, sort of xk plus 1. Okay, so that's basically what's going to end up happening, right? You have Rx is a map from the tangent space to the manifold. It's a map from this tangent space to the manifold itself, all right? And then the basic idea is that for one thing, what you want to do is that you want this map to map the 0 to X and so on, right? And there's some other nice properties you wanted to have. But in particular, if you had the gradient, you know, it's like a negative of the gradient, as we sort of discussed, what you would like to have is that when you evaluate f at this point xk plus 1, then at least if you scale this vector by some scalar so that it's small enough, okay, that locally this f value is going to be lower than the f value at xk, right? So there's this idea that it's if eta k is the gradient, that you want that in some sense this retraction is going to sort of tell you to search along a path which is locally descending. Okay, so the function value is like along that curve is going to descend at least for short times. So let me maybe sort of be a bit more precise about this. So the definition is as follows. Right, so a retraction on a manifold M right, is a smooth mapping let's call it an R, right, from the tangent bundle onto M with the following properties. So the first one is this idea that the retraction is going to map the 0 vector to the point itself. So Rx of 0x is equal to x, okay, where 0x is the 0 element of the tangent space at x. Okay, so Txm. Okay. Then the second one is that with the canonical identification, that T0x Tx of m with Txm. Okay, so what I mean by that is that, so if you recall, the tangent space to a Euclidean vector space, right, is identified with the vector space itself. So M is not a vector space, M is a manifold, right? But the tangent space at any point of M is a vector space, okay? So you can look at the tangent space to that vector space, which is the tangent space at x of M, and that sort of can be identified with the tangent space at x of M, okay? All right, and this is because, again, this is a vector space E, if you will, right? So if you think of this as E, it's like you've seen something like that before. Okay, so with this kind of canonical identification, then the differential of the retraction map 0x is just the identity map on the tangent space. It's like to M. Okay, so where this identity is the identity mapping, right? Okay. So more or less what that means is that locally you're not really going to deform anything when you use this or you construct this retraction. So, all right. So this is, you can ask then, it's like, is a retraction related in some way or shape or form to a coordinate chart? And in a sense it is. It's sort of very clearly related to it because, again, what you have is that you have an identification now between tangent vectors, right, in the neighborhood of a point. Well, actually, tangent vectors, it's like in sort of the tangent space at xk, it's like to the manifold, right, with a neighborhood of xk itself, okay? So of course, it's like T xkm is a tangent space. It's a vector space. So you could imagine sort of choosing a basis for it, right? So if you had a basis, it's like for this tangent space, then you could write any tangent vector as in terms of an n-tuple of numbers, okay? And so what the retraction does is that it takes this n-tuple of numbers and then gives you a point on the manifold, all right? And so, and because this, it's like the linearization of that, it's like at 0 is the identity, right? That basically means that, it's like you can evoke the sort of the inverse function theorem locally to invert that relationship. So there's a sense in which a retraction is morally like the inverse of a coordinate chart, right? But it has some additional properties because, again, it maps x to basically the 0, right, in the origin in Rn, right? So that comes from this condition. And then there's some sort of, again, some nice preservation, it's like of the structure here. And then this condition, if you will, it's like more or less, it's like has the property then that if, again, it's like you have a gradient or a search direction, eta k, which is, say, negative of the gradient, that when you, again, evaluate the function, it's like on this point, nearby point xk plus 1, that the function locally is going to decay, right? So more or less, it's like this rigidity condition is important because the rigidity condition is important because you want to have a situation where it's like, again, it's like if you're moving in a gradient direction or negative gradient direction, that the function is going to locally descend. And then this condition that the retraction maps 0, it's like to the base point, it's equivalent to saying that if your search direction is the 0 vector, that the update doesn't change anything, right? So in the linear case, you had xk plus 1 is xk plus tk eta k, right? And if eta is 0, it's like then xk plus 1 is equal to xk. So if you want to do an update like this, right, then you certainly want the property that Rx acting on the 0 vector is just x itself. Okay. So let's in particular look at a bit more this local rigidity condition, the second condition here. Okay, so what do we have, right? So we know that Rx, get a pen. So we know that Rx is a map from Txm to m, okay, on the one hand. And then we also have the fact that, okay, and Rx also sends 0x to x, okay? So you can look at what d of that is. So d of Rx, right, is a map from the tangent space so actually I should say that d of Rx at 0x, right, is a map from the tangent space at 0x Txm to Txm. Okay, right, and then of course that's what you would need. It's like if you had this kind of condition here. Okay, and so the reason why, okay, so it's this map. It's like, and again, if you think of this as being like some sort of vector space, right? This is a map from the tangent space of a vector space to that vector space, and this is where we evoke the sort of identification, the canonical identification between the tangent space of a vector space with the vector space itself, right? So I want to identify this with just Txm, and then if you did that identification, right, then you can talk about whether or not this map, viewed as a map from Txm to Txm, through this canonical identification of Te to E, right, is an identity map. It's like on E or Txm. Okay, so so that's really where this canonical identification is coming, because if you didn't make that canonical identification, then Drx at the point 0, right, is a map from this space to this space. Okay. So, so this is yeah, and then so we want to say that this is just the identity map on Txm via this identification. Okay, so you might ask, well, what is the consequence of this? And so this equal to that is what's called the local rigidity condition. Okay, so what it means is the following. So what does the local rigidity condition sort of say, if you will? Okay. or what are the implications of the local rigidity condition. Okay, so what it says is the following, that if you have a tangent vector, so given some, it's like eta. Okay. So given some tangent vector in Txm, okay, we look for a curve gamma, which is a map from R. Well, let's just call it T gets mapped to Rx T cos C. Okay, so given a tangent vector, what I'm going to do is that I'm going to scale it. It's like by a scalar, and of course, what happens is that when t equals to 0, it's like that becomes the 0 vector. The retraction of this becomes the retraction at x. It's like of 0, which is just x, right? By the first condition for retraction. So you know that this curve has the property that when you evaluate it at 0, this is just x. Okay, so this is a property of such a curve. So, so given a tangent vector, you consider this curve. Okay, and what you would want to have is that this curve has a property that when you differentiate it and evaluate it at 0, it actually is this tangent vector which you started off beginning with. Okay. So given this, I should say that the rigidity condition, sort of local rigidity condition, implies that this condition holds, right? Which is sort of what you want. Okay. So if you have a tangent vector, right, with a base point, you construct this curve, and you have the property that you know, the derivative of the curve at 0 is actually equal to this vector itself. Okay, so that's what the rigidity condition buys you, is that you're going to use this retraction to construct this curve. It's like gamma, right, which has the property that it goes to the point x. It has a tangent that's like at time 0. It's like, which is actually the vector itself you started with. Okay. So, so what happens then is that moving along this curve, right, gamma is sort of analogous, sort of to moving in the direction of the vector field, in the direction of the vector. While being constrained to the manifold. Okay, and that's basically, you know, it's like the reason, it's like why we want to introduce, it's like this retraction in the following way, is that it allows you to essentially search in a particular direction. Okay. All right. So besides turning sort of, you know, tangent vectors, it's like in the points in the manifold, right? The other important property of, you know, it's like the retraction then is to convert the cost function, right, which is normally a map from the manifold, it's like to the rails, to something which is a map from the rails to the rails. Okay, so this is analogous to what happens in line search algorithms. So line search algorithms, as the name implies, it's like involves you searching. It's like along a line. Of course, a line is parameterized just by R, right? So the point is that line search algorithms sort of reduce the problem of optimization on high dimensional spaces possibly nonlinear to sort of a minimization problem on just the rails, right? So you want to do something similar here. Okay, so given the search direction, okay, which is in, say this, right? I can consider the following. I need a search direction and a retraction, right? Let's call it R, right? I can consider the following. So I can consider f hat x, okay, which is just the composition of f with the retraction. Let's just put it at k. Right, so what's happening here, right? So the retraction is no, that's not what I want to do, right? Sorry. Okay. So given a search direction and a retraction, what I want to do is the following, right? I want to have a map from t to t times the search direction. Okay, so this is in the rails, this is in the tangent space at xk of the manifold. I can apply the retraction to it to give me something that's like on the manifold itself, right? So let me just write it this way, r x k t c, right? This is on the manifold, and then I can apply f of this. This is in the rails again, okay? So the composition, it's like all of these things where you take t multiplied by this search direction, you take the retraction of that, and then you evaluate the function along this, right? Gives you a map from R to R, right? So that puts you into this setting, it's like of line search algorithms where you're trying to minimize a scalar valued function, right, over a domain which is just the rails, okay? So that's basically what's going to end up happening, okay? So the other way to think about this is that if you don't want to think of it from R to R, right, you can also think about it from the point of view of optimization. You know, it's like in the usual linear space setting, right, which maybe is a map from a Euclidean space to R, right? And so if you were to do that, then here you could search over search directions, basically, right? So this is just a tangent space at xk, it's like to the manifold, that is a vector space. So you could try to imagine going from a search vector to its retraction to the function evaluation on that. That gives you a scalar valued function on the tangent space to the manifold, okay? So Right, so before I say that, so this sequence, right, this sort of reduces, so I should say that, okay, so what this does is that given a search direction, right, we obtain a line search which involves minimizing scalar value function over the domain R. Right. Usually you don't search over all R. You just search for something where, it's like the real value is positive and small, right? And that's because if you go very far away from the starting point, it's like then your gradient direction may not be good. It's like, so you really shouldn't take a huge step, but usually maybe you usually search over some sort of closed interval, like say from 0 to 1, right? Or actually half open interval, right? Say 0 not excluding, from 0 to 1, but not excluding, not including 0. Okay, anyway. So, so yeah, I mean, so the other thing you could do, it's like sort of along the lines of this kind of picture here, is you could actually just go from a map from search directions, it's like to real values, and we can ask what that looks like. That sort of leads to a nice concept of what is called a pullback. Okay, so let me try to draw a picture for you again. Okay, so you have a function f, right, which is a map from the manifold to the rails, right, and then you have a retraction, which is a map from txm to the manifold. Okay, so you have a function from m to r, you have a map from txm to m. You can introduce what is called the pullback, right, which is this map from txm to r, which is defined by making the diagram commute, like the f here. Okay, so this is just f composed with rx. Okay, so so this is going to be f hat x, which is defined to be what is called rx star. Okay, f. Okay, so the rx star f is the pullback of f by the map rx. Okay, and it's called the pullback because it starts with a function, it's like on m, and it pulls it back, against the flow of the map rx, right, to a function defined on tx of m. And of course, it's like it's easy to convince yourself that you see this all the time, and there's no real assumption, it's like about rx, except maybe that it's smooth. This doesn't have to be invertible, for example. Okay, and the pullback is sort of well defined. It's like even without having the inverse be well defined. Okay, there's the idea of a push forward. It's like where given a function here, you push it to here. That does require that that map is invertible, but pullbacks are always defined. Okay, so so this then is a scale valued function now on txm, right? So it's a little bit along the lines of what this picture here, this part of the picture here, except that I'm not multiplying by t. Okay, right. So the advantage obviously is that f hat x is a scalar value function on a vector space, right? So I should say this is a vector space. Okay, and then, all right, so this is where explicitly the local rigidity condition comes in, right? is that we're again able to relate the usual gradient of sort of the classical gradient, it's like of f hat of x, with the gradient of f. Okay, so the point is that because of the local rigidity condition, okay, we have the following. Gradient of f hat of x at 0x is equal to just the gradient of f of x. Okay, and of course, as before, all right, so this is always well defined because this is just on a vector space. Here, it's like we need to endow M with a Riemannian metric, right? So here, this right-hand side, we need to endow M with a Riemannian metric in order to make sense of the gradient it's like on the manifold. Okay. So, and yeah. And okay, so the reason why that's true, I guess I should have said, is because so this follows from the fact that the local rigidity condition implies that d of f hat of x at x0 is equal to just d of f of x. Okay. So, well, again, with the canonical identification, that the tangent space at the 0 vector of the tangent space at x of m is identified with the tangent space at x of m. Okay, all right. So those two things are equal. It's like with this canonical identification, so long as you have that the retraction which was used to define this f hat of x, right, has this local rigidity condition. Okay. So, so let me sort of make a remark, right? So you can ask whether or not this retractions always exist, and on a Riemannian manifold they always do, because so the remark is that the what is called Riemannian exponential mapping, right, is an example of a retraction, right, which is to say that it's again this map, it's like from the tangent space at x, it's like to m, it's like to m itself, with the property that you know, r sub x evaluated at a 0 vector is equal to x, and that the linearization or the differential, it's like has this rigidity property that it's essentially the identity map on Txm, right? So those two properties are automatically satisfied by what is known as the Riemannian exponential mapping, okay, which is something you can construct on any Riemannian manifold. But the problem is that you know, it's oftentimes very difficult to compute the Riemannian exponential because, in general, it involves solving a system of nonlinear differential equations. So, in sort of general, right, the Riemannian exponential can be difficult to compute. And so instead of using the Riemannian exponential, it's like we use these retractions in general. And the practical choice of when or what retraction to use, right, then depends on how easy it is to compute, basically, for the manifolds you're working with. Okay, so yeah, so again, the point basically is that it's like, yeah, the point basically is that there always is, it's like a retraction. It's like, but the sort of the canonical choice of retraction, which is this Riemannian exponential mapping, is in general difficult to compute. And so we would like to basically substitute that with a different mapping, right, which is cheaper to compute on the one hand, but still has all the nice properties which are relevant. It's like for the purposes of doing optimization of manifolds and for proving that your optimization algorithm converges. Okay, and the distillation then of the essential properties, if you will, of the Riemannian exponential mapping, which are relevant for it's like, again, the construction of optimization algorithms are exactly the two sort of properties, it's like, which define the idea of a retraction. Okay, so that's basically where we're going with this, and then we're going to talk about retractions. It's like on, of course, embedded manifolds, and then quotient manifolds, and then with that we'll use this to construct line search algorithms on manifolds. Okay, so let me just stop here for now.